In the last lecture, we have seen the harmonic function, and then we have calculated the harmonic conjugate function for the given harmonic function. Now we'll see some more examples based on that. So let's have the example based on harmonic conjugate. So we go with the example. Prove that the function u is equal to half of log of x square plus y square plus sin x cos hyperbolic y is harmonic, hence find the corresponding analytic function and harmonic. Okay, so here we have given a function. This is the given function, and then we have to find out, we have to show that it is harmonic, and then we have to find its harmonic conjugate. Okay, so the solution. So here, as we know, we have to find out the corresponding analytic function also. So we consider let f of z is equal to u plus iv p and analytic function with real part u is equal to half of log of x square plus y square plus sin x into cos hyperbolic y. Okay, so that's what we have. Now we want to find out the analytic function also. We have to show this is a harmonic function also. So to show this, this is a harmonic function, we have to find out second order derivative. To show, to find this analytic function, we have to find out the first order derivatives. Okay, so let us see. We have here, consider, this is a real part. So we have to consider phi 1 of xy is equal to w by wx. So what you will get here, so this is half of 2x upon x square plus y square, and plus this will be cos x cos hyperbolic cos of y. Okay. If we simplify this, we have phi 1 of xy is equal to, this 2 will get cancelled and you will be having x upon x square plus y square plus cos of x into hyperbolic cos of y. So let this equation 1. Now again differentiate this with respect to x. So we have dabba square u by dabba x square. So we have to find the derivative of this term with respect to x again. So here we have to use u upon v rule, and hence we have This is x square plus y square into derivative of this x is going to be 1 minus this x remains as it is. Derivative of denominator is going to be 2x and upon you will have x square plus y square bracket square and the derivative of this term. So it is going to be minus sine x cos hyperbolic y. Remember that we are finding the derivative with respect to x. So this term will be treated as a constant. Now simplify this. So what we get here, dabba square u by dabba x square is equal to. See, this will be x square plus y square minus 2x square. So I'll be having x square plus y square minus 2x square. Upon you have x square plus y square bracket square. Minus we have sine x cos hyperbolic y. So we get here dabba square u by dabba x square is equal to y square minus x square upon x square plus y square and bracket square minus we have sine x and cos hyperbolic y. So let this equation. Okay. Now see, we got the first order derivative with respect to x. We got the second order derivative with respect to x. Now we have to find the first order derivative of this with respect to y and the second order derivative with respect to y. Okay, so let us find the derivative and hence now we have, so we have phi 2 of xy is equal to w by y. So this is again half and you will be having 2y upon x square plus y square plus this sin x remains as it is and the derivative of hyperbolic cosine is hyperbolic sin y. So we are finding the derivative with respect to y. That's why we have to be careful. Now what we get is this phi 2 of xy is equal to y upon x square plus y square plus sin x into hyperbolic sin y. Let this equation 3. Now we want the second order derivative of this u with respect to y. So let us find the second order derivative with respect to y. And hence we have dabba square u by dabba y square is equal to. So it is going to be x square plus y square into 1 minus y as it is, the derivative is 2y upon we have x square plus y square bracket square plus the derivative of this term. So sin x remains as it is and this is hyperbolic cos y. So the derivative of sin hyperbolic sine is hyperbolic cosine. So if we simplify this, what we get is dabba square u by dabba y square is equal to x square plus y square minus 2y square upon x square plus y square bracket square plus sin x into hyperbolic sin y. Okay. Now we can see this is y square minus 2y square and hence we have dabba square u by dabba y square is equal to, it is going to be x square minus y square upon x square plus y square bracket square plus sin x sin hyperbolic y. So this is going to be the equation. So we have be careful. Here we have this is cos hyperbolic y. So it is sin x cos hyperbolic y. Okay. So that's what we have. Now, see, I got the second order derivative with respect to y. I got the second order derivative with respect to x. And so, to have whether this is a harmonic function or not, we have to add this two second order derivative. So, what we can do is adding equations 2 and 4, we get. So, what we are able to get is see dabba square u by dabba x square plus dabba square u by dabba y square is equal to. So what we have dabba square u by dabba x square. This is what the term will be having y square minus x square. Okay. So we have here y square minus x square upon x square plus y square bracket square minus sin x cos hyperbolic y, and this term will be having plus x square minus y square x square plus y square bracket square plus sin x cos hyperbolic y. Now we can simplify this. We'll be having y square minus x square plus x square minus y square upon x square plus y square bracket square minus sin x cos hyperbolic y plus sin x cos hyperbolic y. So this term will get cancelled with this term. This x square will get cancelled with this x square. And here we have minus y square and this is plus y square. So we can say this is going to be 0. Okay. So what we got actually, so we got dabba square u by dabba x square plus dabba square u by dabba y square is equal to 0. So what we say, this is the Laplace equation. So that is, we say the Laplace equation is satisfied. Okay, so Laplace equation is satisfied, and hence we say, hence the function u is a harmonic function. So this is going to be the harmonic function. Now see, we are done with the first part of the example. Okay, so we wanted to show that this is a harmonic function. Now we have to find the corresponding analytic function and its harmonic conjugate. So to find the analytic function, the first step is to write the function. The second step is to calculate the first order derivatives, and then the third step is put x is equal to z and y is equal to 0 in first order derivative. So two steps of Milne-Thompson method already we have completed, and now we go with the third step. So put x is equal to z and y is equal to 0 in equations, okay, 1 and 3. So we get, okay, what we are able to get is phi 1 of z0 is equal to, okay, so what is phi 1 of z0 we have, see here, so this is phi 1, so here I'll be having z upon z square and this will be cos of z, okay, so we get here, this term will be z upon z square plus cos of z. So that we can write 1 by z plus cos of z. So we got phi 1 of z0 is equal to 1 by z plus cos of z. Okay. Now we have to see and phi 2 of z0. So see what we have for phi 2 of z0. Okay, what is the term we have? So phi 2 of z0. Yeah. So if I put y is equal to 0 here, this term will go 0. And this sign hyperbolic y 0 is 0. So this term is going to be 0. So anyhow, both the terms in phi 2 are going to be 0. And hence we write that phi 2 is equal to 0. Okay. So the fourth and final step of Milne-Thompson method by Milne-Thompson method. The analytic function f of z is given as. So I suggest always write the formula. Okay, and hence we have f of z is equal to integration phi 1 of z0 dz minus I integration phi 2 of z0 dz and plus c. So what this is, where c is constant of integration. This is going to be the constant of integration. Now we know what is phi 1 and phi 2. So put up these values here, and hence we have f of z is equal to integral 1 upon z plus cos of z dz minus I integral 0 to dz plus c. So this is equal to integral 1 upon z plus cos z dz plus c. Now we know the integration of 1 upon z. So it is going to be log of z. This is going to be sine z plus c. So we got here f of z is equal to log of z plus sine z plus c. So this is what we have required is required analytic. We got this as an analytic function. Now the second part of our example is completed. We have to find the harmonic conjugate. So harmonic conjugate we need to get. So to get the harmonic conjugate, we have to replace this z by x plus iy. Okay. So what we can do is put z is equal to x plus iy in above equation we get. Okay. So what will have it here? F of z is equal to log of x plus iy plus sine of x plus iy. Okay. And plus c. So what we know is log of z is equal to half of log of x square plus y square plus I tan inverse of pi by x. So this is what the formula we have. Okay, and hence we can write this here as it's going to be half of log of x square plus y square plus I tan inverse of pi by x. And now here we use the formula sin a plus b. So we'll be having plus sin x cos of iy plus cos x sin of iy plus c. So what we know is we know that cos of Iy is equal to cos hyperbolic y, and sine of Iy is equal to hyperbolic sine of y into I. Okay, so we can replace this term and we can replace this term. So we can write this as this is equal to half of, so we have here f of z is equal to half of log of x square plus y square plus I tan inverse of y by x plus sin x cos hyperbolic y plus I cos x sin hyperbolic y plus c. So we can write this as half of log of x square plus y square plus sin x cos hyperbolic y plus I. Here we have this is going to be tan inverse of y by x plus cos x sin hyperbolic y plus c. Okay, so this is f of z. Now the question is whether we got this correct or not. Okay, so how to check whether we got this expression correct or not? So real part is given to us. Check this real part what we have obtained and see the real part what is given to us. If it is same, then we are correct. Okay, so see here that's exactly same, and hence we can say whatever the calculation up to it we have done are correct. Okay, so we got the real part and imaginary part here, and hence we can say comparing real and imaginary part. Comparing real and imaginary parts we get. So what we are able to get here, see, so u is equal to half of log of x square plus y square plus sin x cos hyperbolic y, and v is equal to what we got here. So it is going to be tan inverse of y by x plus cos x sin hyperbolic y. Okay. And hence we can say v is the harmonic conjugate of u. So we write here hence the harmonic conjugate of u is v is equal to tan inverse of y by x plus cos x sin hyperbolic y. Okay. So when we are able to get the harmonic conjugate for, so do you have any doubt in this example? That's great. So if you don't have any doubt, then we'll go to the next example. So we'll go for another example. Okay. So that function v is equal to 3x square y plus 6xy minus y cube is harmonic function, and hence find its corresponding quadratic function and harmonic conjugate. Okay. So here V is given. We have to find the we have to show that it is going to be harmonic function, and hence we have to find the analytic function and its harmonic conjugate. Okay. So let's solve this example. So what we have here, right? F of z is equal to 2 plus ib. B and quadratic function with, so V is given, so obviously we can say it is a real imaginary part. So with imaginary part, V is equal to ex square y minus y. Here we have plus 6xy minus y cube. Okay, so as it is a imaginary part is given, so we start with the first order derivative with respect to y. So what we have here, consider psi 1 of xy is double b by double y equal to, so it is going to be 3x square plus we have 6x minus 3y square. So let this equation 1. We have to prove that this is going to be the harmonic. This is going to be the harmonic function. So we want the second order derivative, and hence we have double square v by double y square is equal to minus 6y. So this is equation 2. And now we have psi 2 of xy is equal to double v by double x. So the derivative of this term with respect to x, you have 6xy plus 6y. Okay, so this is going to be equation 3. And we want to find out the second order derivative with respect to x. So double square v by double x square is equal to, what you can have is, we have 6y. So this is going to be equation 4. Okay. Now, once we have the second order derivatives, to prove that this is a harmonic function, we have to add this 2, and hence what we can do is adding equations 2 and 4, we get. So if I add this equation 2 and 4, then what we are able to get is, see here, so double square v by double x square plus double square v by double y square is equal to 6y minus 6y, and that's going to be 0. So double square v by double x square plus double square v by double y square, this is equal to 0. So here what we get is, we got a Laplace equation. So what we can say is, that is Laplace equation is satisfied. Okay, so once the Laplace equation is satisfied, we can say this is a harmonic function, and hence we can say the function V is harmonic. Okay, so the function V is going to be the harmonic function. Okay, now we have to find the corresponding analytic function. So what we have to do is this is the first step of Milne-Thompson method. Second step also we have calculated. So we have calculated the first order derivatives, and now what we can do, the third step of Milne-Thompson method. So what we have to do in the third step, we put x is equal to z and y is equal to 0. Okay. Okay. So what we are able to get, see the first order derivative with respect to y we have here. Okay. And the first order derivative with respect to x we have here. Okay. So let us put the value of x to be z and y to be 0. So if I put the value of x z here, then I'll get 3z square plus we'll have here 6z. Okay, and here if I put x is equal to z and y is equal to 0, then this term will be 0. So we are able to get psi 1 as to be psi 1 at z0 as 3z square plus 6z, and we have psi 2 of z0 as 0. So we got the third step complete here, and hence we have to go for the fourth and final step of Milne-Thompson method. Okay, and hence what we get here by Milne-Thompson method, the analytic function f of z is given as. So what is the analytic function f of z will be given in the case of imaginary part is given. So we have f of z is equal to psi 1 of z0 dz plus I integration psi 2 of z0 dz plus c. Okay, so where c is constant of integration. Okay, so that's what we have. Now we know psi 1, we know psi 2. So we can have this f of z as integration of dz square plus 6z dz plus I integration 0 dz plus c. Okay, so we can have this is 3z cube by 3 plus 6z square by 2 and plus c. Okay, so we got here f of z is equal to z cube plus 3z square plus c. So this is the required is the required analytic. Okay, so that's what we have. This is going to be the required analytic function. So here we have completed the second step of this example. So we have seen that we wanted to find out the harmonic. We wanted to show that the harmonic function. So we shown this harmonic function. Then we have calculated the corresponding analytic function, and now we have to consider the harmonic conjugate. Okay, so for the harmonic conjugate, we need to put z. So we put z is equal to here we have this is x plus iy in all equations. So equation we have. So what we'll have here? See, this is f of z. So we have here x plus iy bracket cube plus 3x plus iy bracket square plus c. So we can expand this as x cube plus 3 square y minus 3xy square minus iy cube plus 3x square plus 2ixy minus y square plus c. So here what we have considered is I square is equal to minus 1, I cube is equal to minus I. Okay, so that's what we have here. Now, if we simplify f of z is equal to, okay, so what is the term we'll get here? See, we'll collect the term with without I and with I. So we'll have here x cube minus 3xy square plus 3x square minus 3y square plus I dx square y minus y cube plus 6xy plus c. Okay, so this is what we have obtained f of z. Now we have to check whether this is going to be correct or not. So we see what was given to us. V is given to us. So check this V. Vx square y minus y cube plus 6xy. Whether we got this correct or not. If we got this correct, then our answer is correct. Okay. So we see here. This is 3x square y minus y cube plus 6xy. So exactly what was given to us that we have obtained, and hence we can say yes, this is the correct analytic function. So we can write here comparing real and imaginary parts. We have, so what we have here, u is equal to x cube minus 3xy square plus 3x square minus 3y square, and v is equal to vx square y minus y cube plus 6xy. Okay, so we can say the harmonic conjugate of v is u is equal to x cube plus x cube minus 3xy square plus 3x square minus 3y square. Okay. So this is the harmonic conjugate that we are able to get for the given imaginary part or the given function So, do you have any doubt in this example? Okay, no problem. That's great. You don't have any doubt. Okay, good. Okay. So now we know how to find the harmonic conjugate. So we know how to get the function, analytic function when any real part or imaginary part is given. So we are mostly using the Milne-Thompson method to get this all types. Okay, now we have to consider one more concept related to this analytic functions. Okay, so what we know or what is the concept that we need to understand. So the concept is orthogonal trajectories. Okay, so we need to understand orthogonal trajectories. Okay, so the first thing is that what do you mean by orthogonal trajectories? Okay, so orthogonal trajectories of any family of curves. Okay, so what we can say is here we have right f of z is equal to u plus iv be an analytic function. Okay, so these all concepts are related to the analytic function, and hence we need to understand this. So suppose we have this be an analytic function, then what we can have is then the family of curves u is equal to c1 is orthogonal trajectories of the family of curves is equal to c. And we can say, similarly, we can say the family of curves E is equal to C2 is orthogonal trajectories of family of curves U is equal to C. Okay, so what we have here, you can see if I know that the function f of z u plus iv is an analytic function, then I can say u is the orthogonal trajectories of u is equal to c1 is the orthogonal trajectories of v is equal to c2 or v is equal to c2 is the orthogonal trajectories of u is equal to c1. So in the previous examples, we have seen that harmonic conjugate. So what is the difference between the harmonic conjugate and the orthogonal trajectories? Okay, so you can see the main thing that here I'm writing u is equal to c1, v is equal to c2. As in the previous case, I have not written it like that. Okay, and hence, if I consider the harmonic conjugate, it is only a curve. Okay, so if we consider the harmonic conjugate, it is only one curve. Okay, and if I consider the orthogonal trajectories, then I am saying that it is family of curves. Okay, so we have to be careful when we say the orthogonal trajectory or the harmonic conjugate. So harmonic conjugate is only one curve, and orthogonal trajectories are actually it is a family of curves. So there are many curves in the orthogonal trajectories. Okay, in or harmonic conjugate there is only one curve. Okay, now what is mean by orthogonal trajectories? Okay, we say that if this is going to be analytic function, then u is equal to c1 is a orthogonal trajectory of the family of curves to v is equal to c2. So these constants c1 and c2 actually they define the family of curves. Okay, so let us see how these constants define the family of the curves. Okay, now I'll have okay, so we'll have this curves. Okay, so you tell me what these curves are. Okay, so I hope you are able to see these curves. Okay, so tell me what these curves are. What are the curves that I have drawn right now? Show you once again. So what these curves are going to be? You identify these curves. So these curves are the circles. Okay. So we can have these circles precisely. We can say that these are the concentric circles. Okay. So this is a family of curves. So it is going to be x square. We can say this is going to be x square plus y square is equal to c1. So this c1 will decide the square of radius, and according to that we are able to get this curves, these circles. So if I put c1 the value and vary it, I'll get this family of curves. And now we can have the another family of curves. Okay, so we can have uh, this family of curves, the another family of curve like this. So we can see this is the another family that I'm drawing here. So you can see this is the family of lines which we can say y is equal to C2x, because all these lines are passing through the origin. So this is the another family of curves. This is the one family of curves. Okay. So one thing you need to notice that all members of this line family are intersecting all members of this circle family in 90 degree, and each member is intersecting in 90 degree. So this line intersecting all the circles in 90 degree, this line intersecting all the circles in 90 degree, this line intersecting all the circles in 90 degree, or another way we can say all the circles are intersecting with this line family in 90 degree. And so when this happens, that every member of one family intersect with the every other member of the other family in 90 degree, then we say these two families are orthogonal trajectories of each other. Okay, and they are related to the analytic function as the real part and imaginary part. So this is how the real part and the imaginary part of the analytic function are related to each other with the other relation of orthogonal trajectories. So, do you have any doubt in the concept orthogonal trajectories? Okay. So, that's good. You don't have any doubt here. Okay. So,